Hello everyone, and welcome to your second Advanced Swift tutorial. In this tutorial, we're going to be talking about integers in Swift, and mostly just diving into their bit representations and how we can manipulate those bits to do different things. So there's a lot more to talk about the underlying int type and how it's represented in Swift, but this tutorial specifically is really just how are integers in general represented on this system and various other ones, and how can we just sort of see the byte and bit representations of integers. And I think it's just kind of a fun little dive into understanding numbers a little bit more than you might already understand them. So let's dive in. So the first thing I have is a simple sort of extension on binary integer, and it just allows me to print out the either the binary or the byte representations of a number, and we'll come back to that in a little bit. But the first thing we want to do is just sort of play around with creating numbers. So you're probably pretty familiar with this kind of thing already, but let's say I wanted to create a uint 8. I can make one that was 200 like that, and we can see it represented over there. Then I could do something where I try to add another 100 to it, and we're actually going to get an error in this case where we're trying to add a value that's out of its range, right? So this is a fairly common Swift thing where it's very aware of the type values and what it expects and how much you can add before you are overflowing the type. And to avoid this kind of thing, Swift will make you cast essentially the values so that you have a larger type. So the int type, for example, in a 64-bit system would be holding 64 bits rather than the int 8, which only holds 8, and that would only give us a range up to 255, which here obviously we're going to 300. So to fix a situation like this, we would have to make sure that the expected type that we're going to get back is going to have to be larger in this situation. So that's pretty standard, integer construction, and I think most of you are probably familiar with that. There's other things where you can represent the numbers in binary or decimal or hex, right? Decimal is obvious, but so let's just say I want to represent the number 10. So I could represent that in binary. I use 0b to represent that the number I'm representing is in binary. Then we can just say 10 for decimal, and for hex we just say 0x, and then we represent it with 0a in this case. So I could run that, and we can see that I get all 10s out in this representation. Now before I move much further, I just want to give an overview of how binary and hexadecimal representations work. And maybe, if you already understand this concept, feel free to skip ahead in this video, but for those of you who don't, this is a little demonstration. So everyone's pretty familiar with base 10. Base 10 is the decimal system, which you learn in grade school and you use in pretty much everything else other than programming. Or even in programming, but the concept is the same for both binary and hexadecimal. The only thing that's changing here is the base, and this might not be that obvious, but really decimal is a base 10 system, whereas binary is a base 2 system, and hex is base 16, right? And the only thing that really changes is how much we're multiplying the different place values by. So in decimal, we multiply the place values by a power of 10. So 5 in the first place value is just simply 5 times, and if you're in the first place value, this is a power to 0. So 10 to the 0th power is 1. So 5 times 1 is 5. So that's how we have the number 5. 25 would be represented as 2 is in the second place value here, so we multiply it by 10 to the power of 1. And so we would have 2 times 10 in this case, giving us 20. And if we add the 5, which is in the first place value again, we just simply say 5 times 10 to the power 0, which is 1. So we have 5. So 20 plus 5 gives us a value of 25. So decimal, pretty straightforward. We all kind of understand this concept. Now binary is base 2, and this means that each individual place value can only represent 2 values. So we can either represent 0 or we represent 1. These are the only things that we can have in binary. And the way we represent larger numbers is we just change the place value, right? We move or put things in different place values, and we can then multiply them by the base. And the base here is base 2. So 1 is obviously a simple example where we multiply it by 2 to the power of 0, which gives us 1 times 1 is 1. 2 is we would have to move to the next place value, right? The first place can only represent 0 or 1, so we have to move to the next place value to represent 2. So we'd have 2, and that would just simply be multiplying by the base times the index of the place value that we're in, and this would be 1 times 2, which is 2, right? 4, similar example, 9 is basically adding up all the place values, right? So if we have 1 in the fourth place value over here, we have 1 times 2 to the power of 3, and then we add the 1 that's in the first place value, which is 1 times 2 to the power of 0. So we'd have 8 plus 1 equals 9. So pretty straightforward. Hexadecimal is just a continuation of this, where instead of 2 or 10, we're multiplying by 16. And because there are 16 values, and we can only really represent a singular value in a place value, we use letters to represent anything higher than 9. So the numbers go from 0 through 9, and because 10 would be 2 digits, right, and 10 means something else in hexadecimal, so we represent the other values using letters. So we would say 0, 1, if we got to 9, we'd say 8, 9, and then A, B, C, D, E, F, and F would be 15. So if I wanted to represent the number 15 in hexadecimal, it's just an F, and that would be 15 times the place value of 16 to 0, which is just 1, so 15 times 1 is 15. Then, once we've, surpassed all the values in that place value, F is the largest one, then we would move on to the next one with a 1 in the next place value, and that would be 16, because we'd have 1 times 16 to the power of 1, because we're in the next place value over. And it continues the same way like the other examples did, where now we multiply each individual place value and add them together at the end. So that's decimal, binary, and hexadecimal numbers, in case you didn't know. So that's cool, and we'll come back to sort of how these are useful in a little bit. But some things that I just want to show you is how we can see the binary representation of different values. So obviously, well, not obviously, but there is uint8, and the values that uint8 can go from are 0 all the way up to 255, right? It's uint8 is 8 bits, and that gives us 256 possibilities. Then an int 8 would be anything from negative 128 to 127, right? So again, 256 different possibilities, but there's a range of negative and positive values here. Okay, so how could we represent one of these? Well, we could say uint8, and let's just say that I was representing 128. Now I have this nice little binary description extension up here on binary integer, and it allows me to, it's just kind of a complicated way of going through the bits. So it's essentially going through whatever the bit width of the integer that we're representing. And then we're simply, the real important part is really this section here where we're bit shifting, and we'll talk about bit shifting a little bit maybe, but we're simply bit shifting the number by the index that we're in. So that will shift until we get to a particular bit. And then we just take that bit, and that's the thing that we print out. And then we can add spacing or add different results as we choose to, or we are just concatenating that onto the previous result of the reduce. So the details of this, not too important. You can look at this on your own time and play around with it. But I just want to let you know that that's really what this is doing. And as a representation, this is what we would expect to print out if we had printed out uint 16.7, for example. All right, so going back to our example over here, let's do the binary description. And we can see that we get out this binary description of this, right? So this is 128 represented in binary. Now, let's try another example where I say int 8, and obviously int 8 doesn't have the same range, so I'm not going to be able to say 128, and if I tried that, we would end up being notified of that, saying that there's going to be overflow, and we can't do this because it doesn't represent it. So what we can represent, though, is negative 128, and I'm going to do the binary description of negative 128, and interestingly enough, it actually has the exact same binary representation as uint8 does of the same value in positive land. So interesting. And you might be asking yourself, well, how are negative values represented? And to show this, let's just do one more little example here where we do 127, which is this value. And you'll notice that this value is actually one less than this value if I was just looking at the binary representation, right? If I added 1 to this binary representation of 127, then it would actually become this binary representation. And interestingly enough, this is actually flipping around from 127 being the most positive value to negative 128 being the most negative. And the reason for this is how we represent negative numbers in, in computers really, is that we represent them using 1 as the first, the most significant bit rather. If it's a 1, that indicates that we are representing a negative number. So let's look at how this works. So the idea of how we represent these is represented using 2's complement. So 2's complement is really just a way of converting from let's say we had a positive value of 128, or in this case, we're actually just doing 1. So let's say we had the positive value of 1, and I just wanted to get the negative value if it was to be represented in binary. And we were representing it as, the most significant bit if it's a 1 being a negative number. And this is how all negative numbers are represented in binary. So we have, it's a pretty simple kind of formula. You just invert the bits and then you add 1. So here we have the number 1. We inverted all the bits, so zeros become 1s, 1s become 0. Then we add 1 to it, and the outcome would be 1, 1, 1, 1. And this would be the conversion between positive 1, this guy, to negative 1. So that is how we can go about converting from positive to negative values. But the important thing is really just to note that the negative is represented by the most significant bit in the number being a 1. Okay. So with that, I think that pretty much mostly covers how I wanted just to cover the binary description stuff. What I want to show though is how we can use these binary representations to our advantage. So let's say I had a number, and it's going to be a uint 8, and it's going to be 255. Now, there are some databases, for example, and I'm sure there's many other cases where you have a value that maybe only takes signed values. So maybe you're trying to represent this in a uint 8, right? You have 8 bits representing 256 possibilities, but the value that you're trying to save it into is an int 8, for example, which means it can't take anything above 127, right, as a positive value. But you could represent the number using the bits, right? Because both of them have the same number of bits. They are both 8-bit values, and because of that, you can store technically the same amount of information. So what I could do is actually create an int 8, and we can use this fun little initializer on any of the integers called bit pattern, and it just takes the unsigned or signed equivalent, right, whatever the inverse is, of the value. So I could actually pass in b here, and if I run this, you'll see that the value is going to be -1, right? And that was because 255 is all 1s, and all 1s in whatever format you're in is going to represent -1. So we have now represented, we took the bits of this guy, and we used them to create the bit pattern in this guy. And just to show the bits, I'm just going to make a little binary description. So just to show you what the bits actually represent, these would be the bits, and that's what we're storing into the int 8. And if we stored this binary representation, it would be -1. And I could restore this going back the other way, by saying bit pattern again on uint 8, and I can simply take the output of int 8, right? So I can take the bits that we stored in the int 8, and I can resurrect them back into the uint 8 representation, and I'm going to get back 255, which is what I started with. So kind of a fun thing to know is that you don't really need a larger value if you're worried about overflow. You could technically work with the bits themselves because you have the same amount of information stored. They're just stored in a different way of understanding the number. So fun thing to know. All right, with that, let's talk about bytes a little bit. So if I wanted to do, let's just do uint 8, and I'm going to do, I don't know, just do 240, something arbitrary. And then I want to do the byte description that I made up above. We can actually see the description of that, which would be F0 in this case. And let's just change it maybe to do this, for example. And we can see that if it's 250, our hexadecimal representation would be FA, right? So that's what byte description does. It's just representing what we had in our binary representations, right? It's just converting that to be a hexadecimal representation. Now, the reason I'm bringing up bytes is because of how bytes are stored in memory. And it's kind of an interesting concept, not necessarily that useful with Swift directly, but if you are interacting with other systems, there are other ways of how systems store the bytes. And to talk about this, the concept is Endianness. And I'm going to talk about two of the prominent ways that this manifests itself. So imagine we have the number, whatever this thing is, right? So this is a hexadecimal value. The underscores are just for style purposes to separate out the individual bytes. So we'd have, this is a 4-byte number. And if we were to store this in memory, the question is, how does this actually get stored? Because individual bytes, right, have to be placed into memory. And processors do have different ways of storing these bytes. So in Big Endian, we actually take the most significant byte, and that gets placed as in the lowest memory address. So you can see here the 0A would be the most significant byte of this value, and it gets stored in the lowest memory address, right? So the smallest memory address gets the largest value of the number, essentially, the most significant byte. And then we place the other values in the higher ones. So the least significant value gets placed in the highest memory address. Little Endian, although it kind of looks backwards, works in sort of the way that you might understand how the values would be placed if you think of it as the lowest value gets the lowest memory address, right? So in Little Endian, the least significant bit gets put in the lowest memory address. So the smallest memory address in this case would get the D value from this, and then we'd have C, B, A, right? So the individual bytes, again, the least significant byte in this case is going to go to the lowest memory address, and it gets placed from lowest to highest. So these are two different representations that Swift integers understand, and we can actually kind of work with these things directly. So if I constructed a uint16, for example, and I used Big Endian, and I'm going to say 0xff, and then I'm also going to construct the Little Endian, and lastly we'll do just if I did like that. Now if I run this, you'll notice the Little Endian and the standard initializer are going to be the same values. They both treat the number as we would expect the number to be treated, I guess. And the Big Endian, though, is expecting it to be so it's going to take the most significant bytes, right, and it's going to place it as, so it treats the number that you've put in as the order in which it expects it to be reversed, essentially. So that was a bad explanation of whatever that was, but let's make this a little more clear with some zeros. So I'm going to put zeros here, and because it's a 16-bit integer, there's 2 bytes, right? So these would be 2 bytes and these would be 2 bytes. So what's going to end up happening is that the Big Endian is going to switch the values, right? It's going to assume that the least significant memory address, which is actually going to be the FF, even though it's the, it's going to be placed in memory earliest, and it's going to assume that this is the Big Endian representation. So it's going to take the most significant byte and put it in the, from the least, sorry, let's just go back to the diagram so I can point out something. So the most significant byte is in the lowest memory address. So it's going to take the lowest memory address, being this FF part, and it's going to place it into the largest or the most significant byte, right? So it's actually going to swap these values so that it's going to become FF00 effectively as our number. And if we wanted to get the same number, we would just have to put the FF in the beginning. So that would actually represent it as 255 because, again, the most significant byte is going to be placed in the lowest memory address, and so it's going to have to swap these on the initializer. Now, this part's not that interesting to me. What I just want to see is how these are actually being placed. And we can riff off the last tutorial that we did on pointers and actually dig into, well, what does the memory actually look like when we place this down? So to do this, let's do data val, and I'm going to make a int 32 here. And I'm just going to represent a binary number saying 0a, 0b, 0c, and 0d. All right, so that's our 32-bit value. And I'm going to make a buffer pointer. And it's going to be an unsafe raw buffer pointer. We're going to be starting at the value that we're creating here. So we're going to start at data val. And we can use memory layout and get the size of this data val, like that. All right, so now that we have that, we can actually iterate over these values. So I can say element, and we're going to use the buffer pointer, and this is just going to iterate over all the elements that are in the buffer. And what I want to do is print these out, and I'm actually going to use a little bit of a string representation here. And what I want to do is I want to use element, and there's a nice little initializer that you can use. So it's called radix, and it just means how you're representing the number. And if you want to use 16, that'll represent it as 16 bits as your value of basically it's just telling you that it wants to represent it as a hexadecimal value in this case. So you're constructing it with this number that's really going to be, I want to represent this as a hexadecimal value. Anyway, let's go ahead and print this out, and we can see the output. So from my int32, we can see that starting at the lowest memory address, right, because pointers are always going from lowest to highest, at least generally speaking. So I'm going from the lowest value that I have here, and that's going to be the D, and then we have C, B, and A, right? So that's fun. Now what we can do is we can actually convert these integers into their representation. We can switch it into either big or little representations depending on what we want. Now, as you can see, if the lowest or the least significant byte is being placed in the lowest memory address, that means that this is actually being represented as little endian. And if I wanted to switch this representation to big endian, we could just say .big endian, and it'll actually convert that integer and give back the big endian representation. And we can see now that the memory, how this is actually going to be placed, is going to be as a big endian value, where the most significant byte is placed at the least significant memory address. So fun, little bit of information there on how the values are actually stored in memory. All right, let's, as a kind of finish off for this tutorial, I'm just going to go through some different ways that we can construct numbers and manipulate them in different ways. So let's just say I have a larger integer here, and it's going to be 0xff, I don't know, something arbitrary here. And what I want to do is I want to put it into a smaller value, right? So this number is going to have to be represented. Well, it's going to take up basically too many bytes as it stands. So what it's going to take up 2 bytes, and the int8 obviously only takes up 1 byte. So in this case, we can use something though. It's called truncating if needed. And I can pass in a larger integer into it, and it will give me back the truncated value that it can represent. So it's going to take the smaller bits of the number, right? And it's going to truncate anything that came before it. So it's going to remove any of the higher values, and I'm just left with whatever was at the bottom. And to demonstrate this, we can change this to something else, right? And as we can see, we're just taking whatever these smaller bits are in the bottom. It's kind of hard to see it when you're dealing with large values like that. But if I make it a 3, that should be pretty obvious what it's taking in that representation. Okay, so that's what we're going to do if we truncate the bytes. Now, let's do another thing where we're going to talk about overflow and underflow. So if I have a uint8, And it's not really constructing what I want. uint8. So let's say I had the number 255, right, which is the largest integer that I want. And if I try to add 1 to this, right, it's going to basically blow up and say, you can't do this because you're going to have overflow. But there is a nice way to get around this, which is using this operator, which is &add, and it will loop around effectively. So it's going to basically just say, well, if I added one more, the number effectively is going to loop around back to the beginning of what the uint8 represents, right? The smallest value is going to go back to 0. Likewise, if I started with 0 and I subtracted 1, I'm going to go back to 255, right? So these are useful operators if you're trying to maintain a small value in a sort of a smaller buffer or something like that, but you wanted to make sure that you're never going to overflow the value, right? Maybe you're just keeping a counter or a diff, and you have up to, I don't know, like 256 values to loop around on. This is a way that you could avoid the overflow and just keep looping around on the same 8 bits. All right, speaking of some bits, let's deal with a little bit of bit manipulation. So if I had a number of, let's just say 6 in this case, and how can I manipulate this? Well, we can actually move the values around. So if I shift it to the right by 2, I can shift the bits to the left by 2, and we can see the different values here. So what does bit shifting mean? Well, it means I'm literally taking this value, and it's, so if I represented how this would be, oops, that's not the value that I wanted to copy. So if I really was representing this, it's effectively shifting by adding 2 bits here and removing the last 2 bits, and that's how I'm getting 1 at the end of this. Shifting to the left means I'm moving them to the left by 2, and then I'm just filling in with zeros at the end. So that's bit shifting effectively. All right, so some other things we can do, we can deal with bits, we can and or different bits, and if you go back to this example up here, I actually was using an example of anding bits up there. But the reason we generally use this is for, we used to use this a lot in Objective-C where you'd have options and you wanted to check whether options existed or if you wanted to concatenate a bunch of options together. So for example, if you had the bits that we had here and I just wanted to say, I don't know, just add 1 to this, right? I could or the bits that are placed here with the bits that are here, and it just will basically, anytime there's a 1, it's going to fill in the 1 that if there was a 0 in its place, right? So that's how we would end up getting 111 as the end result here. The other thing is anding them. So if I wanted to only see if a particular bit or particular bits are set to 1, for example, I could do this by saying 0, 0. Let's do 1, 0, 0. And this would only take this value out of the bits, right? So anywhere there's a 0, it's going to keep those as zeros, right? It's only going to maintain it if both bits are 1s, right? So that's how the and or operators work. And hopefully that makes sense. All right, that's there's a lot more you can do with bit shifting and stuff like that, but I just kind of want to cover some of the operations. And the last little one that I want to cover, or actually the last 2 I want to cover, there's ways of constructing numbers optionally if they're going to fit in the type that you want. So we saw the truncating if needed one, but what if we didn't actually want to create the number if it was too large, for example? Well, we can do this. We can just say, we can use exactly, and it doesn't matter what I pick, but I can say exactly this particular type. So if I wanted to say only create this uint18 if it's exactly this value, I could say 255, and that should create the value. But if it's anything larger than that, then the value will be nil. So this is an optional or a failable initializer, and it will give me back an optional if it fails to create it, which is very useful to know if you're concerned about overloading or overflowing the integers that you have. And the very last thing I have is on some of the overflow operations that you can do. So you can say, for example, if you have, let's just say I have 16 and I wanted to multiply, And there's a bunch of different ones. There's divide and various other things. But one of the examples I'm just going to show you today is the multiplied reporting overflow. And this will actually give me back a tuple telling me both the result and whether it overflowed the result or not, which is useful to know if you're doing, calculation heavy kind of things. Now, so what I'm going to multiply this by is I'm just going to multiply it by 8. And if I run this, we can see that the value that I get back actually wrapped around. So it'll wrap around to the negative 128. And it tells me that, hey, there was actually overflow with this multiplication. So I multiplied by a number that was too large for the int 8 to hold up to capacity. And it tells me about that in the result. So anyway, that's a general overview of various things that you can do with integers. And I hope it's a nice dive into how their bits and bytes are represented in memory. And if you have any other questions about this tutorial or anything else that you'd like to talk about in the series, leave your comments and your suggestions in the comment section below. And I will see you guys in another tutorial. See you then.